The other idea is to focus on photosynthesis on land instead of the ocean and see if there is a way to either recover the lost forests or add more trees or do some other way to use the photosynthesized carbon and take away the carbon and put it away somewhere. Human beings have, by some counts, have cut down many trillion trees during the Holocene. If you just look at the tropical rainforest and woodland loss since 1750 as a percentage of the value at 1700, we are up here at about over 30% by 2000. But we also talked in the last chapter about how carbon fertilization and human activities and afforestation have now ended up greening the world since about 1982 or so. Of course, there is also the catch that many of that leaf area index increase may be purely agricultural activity, which doesn't necessarily sequester carbon. But if tropical deforestation were a country, it would rank third in CO2 equivalent emissions. So there is China and US, and tropical tree cover loss is here at the third place, with the others following here in terms of gigaton CO2 equivalent per year of almost 6. And this also points to the fact, especially when you consider massive forest fires, wildfires in Australia, in Cape Town, in the US, Canada, and other places, that increasing forest cover is always tricky because there are many issues about their impact on albedo, especially in snow regions where they can drive snow melts, their contribution to isoprenes and other chemicals that can drive ozone production, plus this sudden loss of carbon from forest fires, which are getting worse because of global warming, and generally tropical forest perturbations. And it is now reported that forests like the Amazon are net sources of carbon instead of being net sinks because of all the human activities. So there is a huge debate about whether forests are really saviors or part of the solution. Nonetheless, we have to remember that if we look at the fate of anthropogenic CO2, there is 86% coming from human activities and 14% from land use change, deforestation, all the combinations, and 44% is accumulating in the atmosphere, 29% is being taken up by the forests, land uptake, and 23% is going into the ocean. So it is a substantial sink still. Can we enhance it? We also have to remember that global photosynthesis in terms of gigaton carbon per year here does contribute to taking up the increasing anthropogenic CO2. So there is a carbon dioxide fertilization effect that we talked about. There is increased leaf area index that I just mentioned. And the warming is also giving us growing season change. The spring arrives earlier and winter arrives later. So the growing season is being lengthened to the extent that it can in fact easily be measured. It's a significant increase. So there is room to debate that maybe there is a way to use land, vegetation, terrestrial biosphere to sequester more carbon. So this is a study that looked at global potential tree cover representing an area of 4.4 billion hectares of canopy cover distributed across the world here. Canopy cover percentages are shown here. So you can see some Amazonia, Central African forests, and the rainforests in maritime continent here, and so on. This is the tree cover here in B and C, where global potential tree cover available for restoration is shown. These are slightly different calculations. I won't go into the details. There are also tree potential calculations done by using models for vegetation, the requirements in terms of temperature, precipitation, soils, and other properties is produced, maps of potential for planting new trees, and the idea of planting 1 trillion trees has been making the rounds, and so on and so forth. Nonetheless, it is not a savior either, but additional ideas now include what is called BECCS, bioenergy and carbon capture and sequestration. And the idea is to grow energy crops with high biomass yield, extensive availability, and use the biomass residues where you are sequestering CO2 obviously just through natural photosynthesis, and you are using combustion, fermentation, aerobic digestion, gasification, and so on to convert CO2 for geological storage in saline aquifers and depleted oil and gas fields, and then the CO2 that is now being used for fuel upgrading, gas cleaning, and liquefaction, and to have energy products like heat, biohydrogen, biomethane, synthetic biofuels that we talked about before, electricity, and other non-energy bioproducts. There are ideas of enhancing soil carbon in agricultural land, using more wood for buildings, all kinds of ideas, but none of them really amount to the levels of CO2 drawdown that is required. And the main problem is that the carbon capture and sequestration by plants to photosynthesis is incredibly inefficient. Okay, so that's a very slow way of taking out small amounts of CO2, and even if you use high biomass yield energy crops like this switchgrass and so on, which can grow fast and can be some perennial crops as well, which can be grown again and again without degrading soil and sequestering carbon into the soil along the way, etc., etc. Nonetheless, they don't amount to the level of carbon dioxide sequestration that is needed. Nonetheless, there are other good ideas as well, what is called biochar, where you use methods like pyrolysis to convert biomass, especially grown on degraded land. For example, these can be grown on degraded land or as intercrops, so you have agriculture going on here and you have biofuel crops here. So that gives you a good combination of managing soil carbon as well. This requires energy, but again, you have to be careful, do life cycle analysis to make sure you are sequestering net carbon. So you can extract biofuels and produce what is called biochar, which is a high concentration carbon, which can be it can be put on top of soils, and they can also be used to filter heavy metals and other contaminants and organic contaminants and other fertilizer, nitrogen, phosphate, potash, fertilizer contaminants, and enhance soil carbon. Soil carbon changes soil structure, enhances the ability to keep nutrients and to retain soil moisture, so can reduce drought, increase drought resilience, give you groundwater recharge, and of course increase crop yield in addition to sequestering carbon. So biochar is being used in many places, but again, it's a question of scale. How much can really be accomplished by this? If you look at IPCC scenarios from the last assessment, you will see that BECCS is considered as one of the options in meeting the drawdowns to reach the 2 degrees centigrade temperature targets by 2100. So BECCS is also used in models to look at the various scenarios as to how much CO2 can be drawn down with this approach and so on. But very many people are skeptical about bioenergy being efficient enough with the inefficiency of the trees in sequestering carbon with photosynthesis, in addition to the other factors like albedo and so on. Okay.